So, with that in mind, I'm going to shift gears a little bit to what we're talking about in our next lesson. We're going to focus on the actual going and ordering, the going and getting stuff to make this stuff. So this previous lesson, you've seen like how the welding symbols apply and how you can communicate the stuff. Now, let's say you're the person on the purchasing side. You are actually trying to go out and find the right materials, the right sizes, the right shapes. You're going to go into finding the different components that put it all together. By the way, before I even start the topic, here's a great reference. If you're not familiar with it already, you should be. McMaster Car. What is McMaster Car? You might know? Absolutely. It came from a catalog. I've actually got one of the catalogs still laying around somewhere. But obviously the website takes over. But this is where you can go to find any connector. Just about anything you can imagine in terms of machinery, mechanical components, and get a feel for what they are right here. Okay? So always remember McMaster Car comes in super handy. Tons of connectors. So U-bolt categories, we've got all the different sizes, shapes, styles, everything you can imagine for putting stuff together. And on a mechanical side, manufacturing side, this is a huge deal because connectors drive everything. If we're going to use screws and bolts, if we're going to have socket heads, flat screws, screw types I haven't even seen before. Captive fastener, that's a new one to me. I've never used one of those before. So these are pretty handy. The hex standoffs, we see those in computer technology all the time. So everything you can imagine is all right here for the picking out, the selecting. In fact, a lot of folks, especially on small startup companies, when they're actually doing machinery and tools, they're coming here figuring out what they're going to be able to order in large quantity to put their stuff together. But I want to draw your attention to specifically, what do you notice? What do all of these components right here have in common? They're threaded, right? They work on the threading concept. The wedge and the spiraling, the spiral structure, the helix. So that drives a lot of our connectors, and so that's why we talk about threads and connections in this particular lesson, because it's important for you to understand. It's important for you to be able to look at a drawing and address these kind of things. Let's see. Thread callouts. Whenever you see stuff like this, on a set of drawings, this is one of the crucial things to be able to interpret. Threads. Now, it's great when you just get to go look at a part number. It says, go order socket M3, blah, blah, blah. That's great. But if you're on the fabrication side and you're actually putting this into practice, if you're actually making this stuff, you need to know what this stuff is. So in terms of you understanding, it's all about you being able to read this information. Now, not only do you have to worry about the external threads, you also have to worry about the what? The internal. And by the way, how do we get internal threads? If I take a big piece of plate here, and I'm going to want to use it with a bolt that's like we'll say an M5, or maybe an M10. You've got an M10 socket going to go into there. How do I make this hole receive that bolt? I got to drill and tap, right? So we're going to have to drill a hole right through, and then we're going to have to tap. But what does tapping mean? What does it physically mean? You're going to take a device that actually kind of looks like this. It has like cutting edges, right? That's a horrible drawing, but you get the idea. And you're going to push it down in here, and you're going to turn it. You're going to get some big old torque arms to it. You're going to spin it, and it's going to groove the metal out, correct? So that's the drill and tap process. So obviously you need to know which one to use in comparison to what someone is going to be using in terms of threads. Got to make sure it lines up. Doesn't work out too well to go take an M10 bolt and stick it in like an M8 threaded hole system, right? Now sometimes you'll get the odd characteristic where it does sort of work. Not nearly those size differences, but it does sort of work, but it has a little slop. What happens if threads have slop to them? Like if you have a bolt that you can kind of get in, but it's not tight. Well, it's not the right bolt, but what's actually going to happen? Let's say that you make it work. It's going to strip out. You're basically going to tear out all the internal threading or the socket, probably the internal threading more than likely, more than the actual bolt size. Any idea why that is? Why will the threads internally give out in here before the bolt will? Right, your bolt was actually treated for this process and is hardened up where the plate could just be any grade of plate. So, yeah, it makes it happen in place. Absolutely. So that's all part of the process, is understanding the difference between, you know, this case hardened steel bolts coming and just grabbing an A36 plate of steel. By the way, what does A36 mean? Anybody know? This also factors into your selection of stuff. Okay, so real quickly, ASTM, the American Society for Testing Materials, they basically give standards for all your stuff. So if you go buy a W-beam, you get a choice between A36 and A500. So what those A grades mean is this steel is 36,000 PSI steel. This steel is 50,000 PSI steel. Which one would you rather have your buildings made out of? A500, right? Now, that is typically the case. Most of our steel in our large buildings and stuff, we're using A500 is kind of the standard. Don't get me wrong, though, we still use A36 in some stuff. But the designers have to be very much aware of it because that's a significant strength difference, right? Now, surprisingly, the ductility, the actual, how much it deflects and stuff, that doesn't shift that much. But this is your ultimate failure value. This is where this thing actually starts to break apart and things go bad. So it's important to at least understand the difference, that there are material specifications and standards that do really matter in putting stuff together. Now, if I was back in that earlier situation where I just had that big piece of equipment and it's just about vibration, I could probably go with A36 and be okay. We're not really going to stress this thing because it's a small part. It's not going to be under that much stress no matter how much it's vibrating. But if I'm actually going to go make a building and I'm going to span about 28 feet from here to here, I might be concerned about not only is it going to sag, but also more importantly, where's its failure load going to be? And that's where I'll go with the A500. Anyway, a little side note there. But when you go pick out that stuff, you have to be aware of what thread size, because you're going to strip stuff out if you don't get it right, if you don't get it matching, and you have to really understand what these call-outs are. So, by the way, anybody got the ability to tell me what this call-out is? What's it mean? What am I actually going to go buy right now? I'm going to get an external thread system. This is a thread call-out. About how big is it? I'll zoom it in there for a little bit. But what size? What size hole am I roughly going to be? Half inch. How can you tell? 0.5. So your major diameter is typically what we consider sort of that bolt size, the major diameter. Now then we got this 13 that follows up. What's 13 mean? Thread pitch, which means what though? Right. Now notice there's a big difference between the English standard thread per inch and what we deal with metric. Totally two different categories. They don't line up. All right, just keep that in mind. That'll come up later. Then we got this UNC, which is, what type of course or what type of threading system is it? And there's two versions of this. There could be UNC and there could be UNF. Anybody know what the differences are? Okay, so we got the terms coarse thread and fine thread, but what does that really mean?
Usually the thread pitch is a lot higher on fine thread, and you see it more in this application.
Yeah. All right, so let's say we got a UNC, and I'm just going to kind of draw it out and compare that to a UNF. For the same amount of inches, you can see that the number of the thread count increases. Any reason why we would bother doing this? Why would we bother why aren't these coarse threads nice and big, strong? Why don't we use those all the time? Which one's actually going to give me the more holding power? Right, because you get more wedges in there, right? So you get more connections. So UNC, UNF, big deal. Obviously it means just as much internally in terms of tapping as it does bind. So we got that. We've got our basically class of fit. If it's got an A, typically 2 is what you see a lot. You got your internal thread, external thread represented by an A, and then of course, what represents an internal thread? Yeah, B. And then we got your length, and most of the time no one actually says long at the end of it. They just assume that you get that. Now there is one component that has been left out of this callout that is assumed it's left out for a reason. LH. Left-hand thread. So if you don't see anything, you always assume it turns which way? The right hand. If they actually need to be reversed, then they'll give you the LH. Okay? So that is one of the big deals about this particular lesson. It's not only the material shapes, types, how they connect together, but also how you use these threads to make stuff work. Because make no mistake, no matter what you're doing, big or small, these threads and how they perform really, really matter. Overall science is this. We use the thread system to create friction. So just to put in perspective, I've got two plates here. I want to maximize my resistance to movement. So if I'm pushing this plate this way and pulling this plate this way, I want to maximize my ability. Now, back in the day, starting off when we had rivets and stuff like that, we just used the rivet to actually stop this motion, you know, by its raw strength in size. Nowadays, we actually use the threads and the connectors to not only help resist the motion, but also to bite down here and here with that torquing ability. You know, we tighten, we tighten, we tighten, because we want these two plates as tight together as we can possibly get them within standards. And why is that? Why do we want to sandwich these things together super tight? Friction. We basically create internal friction, which also helps resist the motion. Okay? That's why we have all these standards about how much you're supposed to tension your bolts and things to. You actually, in actually ideal scenarios, you get these things up to right about to the point where they're going to fail. Right within, in an ideal theoretical world, we want this right at that breaking point, because that means we're getting the absolute most friction value we can, and the bolt's not doing that much. But obviously we have a safety factor. We don't want you to tighten them that tight, because what eventually happens? They just shear apart, and then you lose everything. So, but when they're tightened down, that friction becomes so strong that bolt's technically not doing much in terms of resisting across its shear plane. So a little thing to keep in mind there. All right, so questions on threads that you want to ask. It's going to all tie in together. It's all about selecting the parts and getting the stuff done, and that's what your particular lesson is all about. So